Welcome back, everyone. So in this lesson, we're going to start talking more about the quantitative relationships between reactants and products in chemical reactions. So we've already had an introduction to this when we first started learning about mole ratios in a previous lesson. And we're going to go back to that concept and build upon it so that we can learn some more about the quantitative aspects of chemical reactions. And we're going to learn about things like chemical yield, percent yield, and limiting reactants as we go through this. Today, though, we're just going to get started sort of reviewing this concept of mole ratios and then looking at a few really simple types of stoichiometry problems and what those look like and how we can use the mole ratios, molar mass, and the concept of the mole to help us answer these simple quantitative questions. So let's get started first reviewing the concept of the mole ratio. So as you've seen already, mole ratios are pretty straightforward. Essentially, we write a balanced chemical reaction down, and the coefficients that are present enable us to prepare various conversion factors that are built into the chemical reaction that we're talking about. So if we have some starting materials and some products and the coefficients that go along with them, we're able to easily interconvert between those starting materials and products using the coefficients that are present in a balanced chemical reaction. To show you what I mean, let's get started with an example reaction. And I like to use the example reaction using iron metal. So the example reaction that I want to write down the balanced chemical formula for and then get some conversion factors for is this one. It's iron metal is combusted to form iron 3 oxide. So let's write that down and see if we can come up with a balanced chemical reaction, and then let's look at the conversion factors that are present for that chemical reaction. So we're going to get started just by writing down the element names. So iron is Fe, that's elemental iron, and oxygen is the symbol O. And then we're going to combine those two because we're doing a combustion reaction. We're combining iron metal with oxygen, that's the combustion reaction format. And then we get the ionic compound iron oxide. Now I'm going to go and do the subscripts here as well and the states. So iron is a solid, so it gets the S. Oxygen is diatomic, so it gets the subscript 2, and it's a gas. And then I'm showing here on the right how we come up with the subscripts for iron oxide. Now we're told that it's iron 3 oxide. That means iron has a 3+ charge. So in order to have a charge balanced compound with oxide, which is 2 negative, we need to have 3 oxygen atoms and 2 iron 3+ cations. If we have this combination, we'll have 6 positive ions charges and 6 negative anion charges. Those will add up to 0, so we'll have a neutral compound, and we have the subscript 2 next to iron and the subscript 3 next to oxygen. This is iron 3 oxide. Now, of course, we're not finished because this is unbalanced. Notice that we have 3 oxygen atoms in the product, however, there are only 2 indicated in the starting material for oxygen. Also notice there are 2 iron atoms in the product, but we only have 1 over here on the reactant side. So to balance this out, I'm just going to have to adjust the coefficients in front of each of the starting materials and the product in order to make sure we have the right number of atoms on both sides. So if we look at oxygen on the product side in iron 3 oxide, notice that we have an odd number of oxygen atoms. We can make that even, and it will make the balancing quite a bit easier. If we put a 2 coefficient here, that means we have a total of 6 oxygen atoms. On the product side, we can make that equal by putting a 3 over here. That balances oxygen on both sides. Now we just have to make sure that iron adds up as well. Notice that we have a total of 4 iron atoms over here. Let's just make a 4 right here in front of iron. So now this is a balanced chemical reaction. And from this, we can construct a number of conversion factors between iron, oxygen, and iron oxide. So for example, let's suppose we needed a conversion factor that would allow us to convert between iron and oxygen in this reaction. So suppose I had 100 grams of iron and I wanted to know how much oxygen would be required to combust all of it. I would need a conversion factor to do that. Or conversely, what if I had, say, 100 grams of oxygen and want to see how much iron I could combust? I would need a conversion factor for that as well. And this is actually what stoichiometry is. It's the use of conversion factors based on the balanced chemical reaction and the coefficients that are in that balanced chemical reaction. So for example, I can make a conversion factor between iron and oxygen like so, where the blank spaces there are actually the conversion factors in the balanced chemical reaction that I came up with. So for iron, we need 4, and for oxygen, we need 3. So now I have a conversion factor that enables me to convert, say, from oxygen into iron or from iron into oxygen. Now let's look at making a conversion factor between the starting materials and the product. So first off, notice we have two different starting materials. We have both iron and oxygen, and we only have one product. So we would need a conversion factor for, say, from iron into iron oxide. That would be one conversion factor using the coefficients 4 and 2. And another conversion factor would be between oxygen and iron oxide. And those would have different coefficients. So we have 3 and 2 for that. So let's write down those conversion factors as well. So we'll start by looking at the conversion factor that exists between oxygen and iron oxide in this reaction. So we have the coefficients that we need to put in before oxygen and iron oxide, and notice that for oxygen it's 3 and iron oxide it is 2. We can also write a conversion factor between iron and iron oxide. So again, the missing spaces here just represent the coefficients in the balanced chemical reaction. So we have the coefficient 4 in front of iron and the coefficient 2 in front of iron oxide. So that's a review of mole ratios and how we balance chemical reactions to find mole ratios. Now what we're going to do in part B is we are going to learn how to use these conversion factors to solve some simple stoichiometry problems. So let's see how we go about doing this. The first type of problem that we will commonly see is we are given some kind of a reaction and we need to find out if we have some number of moles of one of the materials, say one of the starting materials. From that information, we want to be able to find out how many moles of, say, some other thing in the reaction, like the product or another starting material. So essentially, we need to go from moles of one thing into moles of another thing. This is basically interconverting different mole quantities, different quantities of moles of A into moles of B. A format of a question might look something like this. How many moles of product B can be made from reactant A? Now, because we're only converting between moles, mole quantities, so moles of A to moles of B, or vice versa, moles B to moles A, we're not involving mass at all. There's no question of how many grams of A or how many grams of B. And for that reason, we don't need to involve the molecular masses of our compounds. We only have to use the coefficients from the balanced chemical reaction to solve these types of problems. So to see how this works, let's take a look at the first example. So in this example, we need to determine how many moles of iron oxide are made if we have 6.25 moles of iron. So essentially, we're going to convert moles of iron into moles of iron oxide. So let's start with our 6.25 moles of iron and then use a conversion factor from the balanced chemical equation to enable this conversion. So we write down 6.25 moles of iron and then multiply that by a conversion factor. The units on the bottom of this conversion factor should be iron. That's our original unit. We're converting into iron oxide, so that will be on the top. And then we just need to fill in these spaces with the correct values coming from the balanced chemical reaction. So if we go and look at the conversion factors that we derived for this, the coefficient in front of iron is 4, and the coefficient in front of iron oxide is 2. So now we can go ahead and solve this by taking 6.25, multiplying it by 2, hitting equals, and then dividing by 4. And you should get 3.13 moles of iron oxide. So let's take a look at another example. In example 2, I have this question here, which is how many moles of iron would be needed to make 5.75 moles of iron oxide? So it's exactly the opposite as before. We're starting with moles of iron oxide, but converting them into moles of iron. So we're going to go from moles of iron oxide into moles of iron. So we just need to set up our conversion factors in the correct sequence. So our starting point is the 5.75 moles of iron oxide. And since we're converting into iron from iron oxide, we're going to have moles of iron in the top position of the conversion factor and moles of iron oxide in the bottom position. Now we need to place our coefficients into these blank spaces here. Notice that it's 4 for iron and 2 for iron oxide. So we take our 5.75 moles of iron oxide, multiply it by 4, hit equals, and then divide by 2, and you get 11.5 moles of iron. So that's how we interconvert between different quantities involving only moles, so moles of starting material to moles of product, or vice versa. Now, on the next page, we're going to learn how to solve problems that involve mass conversions. So if we have a mass of a starting material and we need to know the mass of a product, or vice versa. So let's turn to the next page in the notes and see how that works. So this is the format of a typical problem that involves mass stoichiometry rather than just moles. The format might look something like this. How many grams or kilograms or milligrams of product B can be made from some number of grams or kilograms or milligrams of reactant A? So you're given, say, the mass of the reactant and you need to know the mass of the product. Or you might be given the mass of the product and be asked what was the mass of the reactant used to make it. So how do we solve these types of problems? Well, the basic process is outlined down here. The first thing to note is that we don't have a direct conversion factor between the mass of A and the mass of B. We have to go through some intermediate stages. The first stage is we convert our mass of A into the moles of A. And to do that, we use the molecular mass of A as the conversion factor. After we have moles of A, we're going to convert moles of A into the other material, so moles of B. Now, we just saw how to do that. I call this crossing the mole bridge because we're going from the moles of some known compound into the moles of some unknown compound. So moles of one thing into moles of another. And we do this, of course, using the mole ratios that we built from the equation, just like in the type 1 problems we saw on the previous page. So now that the moles of B have been established, it's a simple matter to convert moles of B into the mass of B. To do that, we just use the molecular mass of B as the conversion factor. Let's take a look at this first example. How many grams of iron oxide could be produced from 2.50 grams of pure iron? So looking at this problem, we need to convert the 2.50 grams of pure iron into grams of iron oxide, which is the requested quantity. Now, as I mentioned above, there's no direct conversion factor that enables us to go right from this 2.5 grams of pure iron into grams of iron oxide. The first thing we need to do is convert grams of iron into moles of iron. Once we have moles of iron, we can then cross the mole bridge and convert moles of iron into moles of iron oxide. Then once we have moles of iron oxide, it's a simple matter to convert that into the grams of iron oxide. So we have these 3 steps to do in order to get from grams of iron into grams of iron oxide. So in this first step, we're just going to use the molecular mass for iron to convert grams of iron into the moles of iron. So MM stands for molecular mass. That's step 1. Step 2, crossing the mole bridge. For this step, we use the coefficients from the balanced chemical equation that allow us to interconvert between moles of one thing and moles of another thing. And then finally, step 3. In step 3, we use the molar mass of iron oxide that allows us to convert between moles of iron oxide and grams of iron oxide. So 3 steps. Let's set these up. So the first step is let's put in our starting point, which is the 2.50 grams of pure iron. Next, we set up a conversion factor that allows us to go from grams of iron into moles of iron. Now, what value do we put in here? Well, we have 1 mole of iron, and then we look at the periodic table and we see that the molar mass is 55.85 grams for every mole. So we'll put that value in there. Now here in the second step, we're converting between moles of iron and moles of iron oxide. So moles of iron oxide is our destination. That's where we're going next. So that unit will be on top. And moles of iron is on the bottom. That's where we're coming from. Now the third step. The third step is we're going from moles of iron oxide into grams of iron oxide. So we need to have the molar mass for iron oxide present. 1 mole of iron oxide turns out to be 159.69 grams. So 159.69 grams per mole. So we'll put that value in there. Now to complete this, we just need to have the coefficients from the balanced chemical reaction so they can fill in the mole bridge conversion factor that I have there in step 2. So if you look at the equation, you'll see that the coefficient in front of iron oxide was 2 and the coefficient in front of iron was 4. So we have a 2 and a 4. Now we can solve this. So if you plug in 2.50 divided by 55.85 and then multiply that by 2, then divide by 4, and then multiply that by 159.69, you should come up with 3.57 grams of iron oxide. So if we have 2.5 grams of iron, we can convert that into 3.57 grams of iron oxide by combustion. All right, let's do one more example of this. What if we had to go the opposite direction? So in this example, we see how many grams of iron, which is the starting material, would be needed to make 3.25 grams of the product. So we're going from the product to the starting material, our product being iron oxide. So we don't actually have to do anything different. We do these same 3 steps the same way. We just need to make sure we use the right molecular masses and the right conversion factors with the correct sequence and setup with the conversion factors. So our first conversion factor allows us to go from grams of iron oxide into moles of iron oxide. That's step 1. Step 2, we go from moles of iron oxide into moles of iron. And then we go from moles of iron into grams of iron. So we have the same 3 steps. In the first step, we're using the molecular mass of iron oxide. So we need to know what the molecular mass is. 1 mole of iron oxide is 159.69 grams. So we can put those values in. In step 2, we're going from moles of iron oxide into moles of iron. These are the coefficients from the chemical reaction, and it's crossing the mole bridge. Remember, we have 4 moles of iron for 2 moles of iron oxide. And then finally, the third step, we use the molar mass for iron, which is 55.85 grams of iron for every mole. That's from the periodic table. If we plug this into our calculator, we should get 2.27 grams of iron. So what this is telling us is that we would need 2.27 grams of iron to make 3.25 grams of iron oxide. Now it turns out, of course, that not all reactions are 100% efficient. In the next lesson, we will learn how to take this into account. We will also learn that there are situations in which you don't have enough of one of the starting materials to react with all of the other starting material. We call these limiting reactant problems, and we'll learn how to handle those as well. So for now, that's the end of this lesson. Please let me know if you have any questions, and I'll see you soon.